Okay. All right. In this part of the video, we are going to be deriving an expression for heat diffusion for a spherical surface. So, what we're going to do is examine this spherical equation that I've made, and we're going to try to make some heat diffusion equation for it. So, I've done a lot of the setup for this equation in advance, just because it takes a lot of time to set all this up. So, we have this. I'm gonna circle this in green just so it's obvious. We have this three-dimensional object that's being kind of projected up from a spherical unit, and it's just one part of that. And so we observe that there's some radius from the distance of that object between whatever distance there might be from the origin. We know that there is a change of angle in this case, d of theta, which is just the angle of the arc length in this case. And we have some change of distance from the y and z, no, x and y axis, which we're going to call phi in this case. And we have a change of phi that we're defining as r sine, which I'll get into justification of that for a little bit when we start going over what the shadow is over here. But all you need to know is that this is change of phi over here. We have change of theta. And for our actual system, we have the change of radius, which is just the side of this three-dimensional object. So when we're trying to find, in this case, a heat diffusion equation, we have to find the volume of our system. We have to find d of v. So for this object, it's pretty easy for the first half because we have our arc length side multiplied by our change of angle, and then we can multiply this by the change of radius. However, where it gets difficult is the third side, which you can kind of see. I'll again kind of highlight because it's hard to tell. You have this side of three-dimensional object. I'm projecting it down with this shadow over here just to make it easy to write down. In this case, we know that there's some radius involved, so it's going to be multiplied by r. Uh, this is an arc length of a object. And so you have to consider the sinusoidal relationship with that for an object like this. So we know it's sine. We know the angle in this case is, uh, in this case, it would be theta based on our diagram. And we know that this would be in regard to the change of this direction, which is we're calling phi in this case. So change of phi. So when we add this all together, we multiply this by r sine of theta and then d of phi. We underline this. So now if we combine like terms, this is r squared sine of theta, d of theta, d of r, and d of phi. So this is our volumetric expression, and now we can multiply this with our energy storage and energy generation expression. Energy storage. Sorry, this keeps happening. Nope, that's the wrong one. Sorry. We have our energy storage equation, which looks like this would be change of temperature due to change of time multiplied by density, heat capacity, and this volumetric expression. And then same thing for Q. This is heat added or heat net multiplied by r squared sine of theta, d of r, d of phi. So now we have our expressions for energy stored and energy generation, but this is the lengthy part of the problem. We need to find the net heat flow, and we have to do this for each Cartesian direction like how we did in the first part of this homework assignment. So what we're going to do is observe the change of heat throughout each direction. And we're first going to start with R. Now, something I'm going to do is I'm going to make a little diagram that's just kind of like repeating our structure over here. So if we're entering through R in this case, R goes through something like this. We have our R and then we have R plus D of R. We're going to make this Q. So this is our heat entering, Q of R, and then our heat leaving, which is QR plus D of R. We know this part, this is linear approximation. Uh, Q net equals Q in minus Q out. Q out equals, with a linear approximation again, this is QR plus D of R, which roughly equals Q of R plus the change of Q of R in regards to change of R multiplied by D of R. So when we do this, we get negative change of Q of R over change of R multiplied by D of R. And now we apply Fourier's law. And the reason why I drew this is because I wanted to make a quick area observation. The cross-sectional area in this case is RD of theta. And for this bottom sign, it's the sign relationship that we made, which is sine. I think it's because I need to plug this in. Hold on. I'm gonna plug this guy in. I think it's just taking a lot of power and it needs power. Make sure everything looks good. Okay, everything looks good. So we have Fourier's law in this case, and when we apply that, we get negative QQR. And oh, sorry, I forgot. We were going with this area expression. Delta phi. And now when we multiply these two terms, we'll get an area expression. So we remember this is the negative thermal conductivity multiplied, and we did the analysis here. This is R squared sine of theta d of phi, and this is multiplied by d of t over change of R multiplied by d of R. Or if we want to simplify this, this turns into partial change of R k multiplied by, I'll leave R squared in here, dt over d of R, and then this is multiplied by sine of theta, d of theta, right? Did I miss an area? Oh, yeah, yeah, for the original part here, this is R squared, and then d of theta is also in here for the area expression. And then d of phi, and then d of R. So you notice we're already seeing kind of a similarity with the volumetric relationships here. We're going to keep proceeding, and we're going to see that every part of the net flow is going to be, or for the heat going in, is going to be different in this case. So now we're going to go ahead and look at it from the theta direction. So again, I'm just going to keep drawing this. It makes doing the area for this a little easier, even if it's not super pretty. So we're going to theta now. And theta in this case is coming in from the top and leaving the bottom. So this is our theta sign. I'm just going to in advance kind of do the area. This would be d of r multiplied by r sine theta d of phi. Okay, so now we're going to do the same justification. We have q of theta going in, and we have q of theta plus d of theta leaving our system. Uh, this is the same song and dance. Eventually, the Q net equals negative change of Q theta over change of theta multiplied by, in this case, it would be d of theta. So that's what we get for a Q net of theta. Now, we do have something different with Fourier's law when we apply this. So right now, the problem is if we applied Fourier's law right now, if we applied Fourier's law now, the units wouldn't exactly cancel out pretty. Remember, when we did Fourier's law, it's temperature over some distance. We're in radians right now. Radians is not the same thing as distance. So in order to cancel it out, you have to multiply it by the radius when we do the temperature gradient. So I'm gonna write this out. Theta. Okay, these two turns into positives. And this is going to be multiplied by the area in this case, which we said was r sine of theta d of y multiplied by d of r multiplied by the change in temperature. And again, we're going to be multiplying the change in theta by the radius to then convert the radians into a unit of length so that units can cancel out properly. And then this will be multiplied by d of theta. So when we simplify this, we get something that looks like d of d theta multiplied by k. This will be uh r's cancel out here. So we get sine of theta multiplied by d of t over a change of theta multiplied by d of phi, d of theta, and d of r in this case. And then now we're going to go ahead and do I'm going to go ahead and section this off just so I don't get like confused. Don't want to have incorrect units because I was being lazy. Okay, so we have our expressions. Now we're going to go ahead and do the last one, which is going to be phi in this case. So I'm going to make our three-dimensional object. Now we're coming in for phi in this case, which is coming in, it's going to go through this side over here, which this is going to be d of r multiplied by, this is r d of theta. So it's going to be r d of theta d of r, just to kind of have a radius before it begin. And then same song and dance, this is going to be the q net of phi, which just equals the negative change of the heat due to phi over change of phi multiplied by d of phi. So we're going to apply Fourier's law. Wasn't anything important. Just making sure. So now we're going to apply Fourier's law to this. And when we do, phi is in a unique situation where it is an arc length in this case. And so to turn that into a type of length, you not only have to multiply it by the radius, but you also have to multiply it by the sine multiplied by the angle in this case, which we said was theta. So it's going to be similar to the previous problem, but a little different. Change of phi multiplied. I'm just going to remove the negatives because I know they're negative at this point. Okay, and then we have the area of this, which is r d of theta multiplied by d of r. And then this is going to be multiplied by the temperature gradient over r sine of theta. Yes, r sine of theta multiplied by the change of phi. and then this will be multiplied by d of phi. And then if I want to move everything, the way I'll do that is I'll do change of phi divided by k. Sorry, I had to make sure I was doing my algebra right. I wasn't super confident, but I am now. The r's cancel out here, and we're left with d of t over d of phi is then multiplied by 1 over sine of theta, d of theta, d of phi, d of r. Okay, so we have all of these net heat equations. So now what I'm going to do is I'm going to add them all together and simplify them and then introduce them back into our energy stored and energy generation in this case. So when I do that, I'm going to take like terms. I'm going to take, you know what? No, 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 no. Let's not do it like that. That's lazy. I'm going to look at all of them and I'm going to simplify them in regard to the energy stored and energy generated. So what I'm going to do is let's duplicate this. I think that's going to be the fastest way. So now I can erase everything and just focus on the equations that we've extracted. All right, so here's what I'm going to do. Go ahead, move all these equations together. We have the energy stored set equal to our, oh, you know what? No, that's not what I'm going to take. I'm going to take this part of it. Those Q nets. Now I'm going to go ahead. Sorry, that is neighbors. Cannot do anything about that. Oh, you know what? I think I accidentally erased one of the parts here. I think this is supposed to be change of R. There we go. Okay. And then move this part over here. Okay. Now we can finally start doing some work. So we have all these terms together. They're all cleaned up nice and pretty. So now we're going to go ahead and begin simplifying all terms. So when we do this, we know that there's a lot of d of sine, d of theta, and d of r. So firstly, I'm going to begin canceling those out in each term. And now I'm going to look at how the sine of what happens if we divide every side by r squared of sine theta. So if I divide 1 over r squared sine of theta, it cancels out sine of theta, and we're going to leave the r squared in front just for now, but that simplifies pretty easily. Now we're going to divide this side by r squared sine of theta. When we do that, we're still over r squared. And this sine theta is not the same as this one in here, so we're going to go ahead and leave that into that term. And then when we do this with this side, this adds r squared, and that adds a square to sine of theta. I wanted to make sure that I was assuming something which I actually wasn't at first. Thermal conductivity in this case, we're assuming that it's constant throughout our system, just for the sake of simplification for our expression here. Forgot to say that earlier. But now what we can do is take K out, and when we divide by our density and heat capacity on every term, we should get, in this case, it would be alpha in this case. So now what we can do is have a final simplified expression of dt d of t equals, in this case, it would be thermal conductivity, and this would be multiplied by, okay, sorry, I just got a notification the meeting will end. Uh, 1 over r squared multiplied by r squared, the derivative of time, change of r squared. And then this would be plus 1 over r squared, and this sign moves forward because they are the same expression. This would be the double derivative of time due to change of theta squared, which is the double derivative. And then this would be plus 1 over r squared sine squared of theta multiplied by the double derivative of temperature gradient over phi in this case. And then we add this with the energy generation equation. All right, so that took a lot of simplifying, but essentially this is the same type of heat diffusion equation that we've solved for, except now our double derivatives are in terms of a spherical unit that we have solved for, as seen over here, with every direction accounted for, and we had to make corrections for theta and phi for them being in radians and arc length respectively. So for the next part, we'll be focusing on the simplification for uh, for a type of problem and then compare that to electrical circuits to show that thermal resistance is analogous with electrical resistance. All right. Before we continue, I wanted to give a brief addendum. This is the corrected form of the equation. In the previous part, I had incorrectly created a double derivative for the radial and what is this? The I did it for the radial and the why is the word leaving my brain? Theta side. Sorry, I don't know why that word left my brain. I did it for the radial and theta side. That is incorrect. You're supposed to leave it out fully in this case. So I just wanted to give that brief correction really quick before I proceeded because that was the incorrect number. So we're given a question where we have no heat generation, steady state, and heat flow only in the radial direction. And we have to find an expression for the equivalent thermal resistance that is similar to a voltage expression in terms of expressing resistance due to a current. So let's go ahead and start with the assumption that we are in steady state. that there is no heat generation and that it is only radial heat being transferred. Okay, so with these assumptions, we know that generation equals zero. We know that the phi and the theta heats also equal zero, and that our change of temperature due to time is zero. And we know that uh there is no what is it? There's no heat diffusion coefficient present in our system. And we also know that the 1 over r squared in this case is irrelevant because this would just multiply to zero. So our final state in this case is going to be 0 over du of r multiplied by r squared over our temperature gradients due to our radial distance. So we're left with an equation like this. And the whole point of this is that we're going to try to separate our change of temperature with Q and some thermal resistivity uh, to show what the resistance of our system looks like, our thermal resistance to be specific. So if I integrate both sides, I get 0 equals r squared divided by our temperature gradient plus C1. This C1 becomes very important as we proceed. So in this case, we would say that we're going to move C1 to the other side, and it remains positive because it's constant. And then we can divide both sides by r squared and multiply by d of r. The reason why we're doing this is because we're just moving like terms to either side so that we can further integrate and get that change of t that we want. So we're going to get C1 r squared d of r equals change of temperature. We're going to integrate both sides and we get negative C1, which is positive. It can be positive or negative. I'm just going to keep it positive. R plus C2 equals our uh, temperature due to radius. So with this, we're going to apply Fourier's law. We're doing this for two reasons. One, we want to find the C1 value, and two, we want to put heat flow into this. We want to put Q in here because that's going to be our current in this case for the equation. So Q equals thermal conductivity, and then the area of a sphere would be 4 pi r squared, and then multiplied by d of t of d of r. Now, I kind of did this part fast, but if you look, dt over d of r equals C1 over R squared. If you do the algebra for this, you can actually express dt over d of R as C1 over R squared. And when you do that, you get thermal conductivity times 4 pi R squared multiplied by C1 over R squared. The R squared is canceled out, and now we have Q equals K times 4 pi multiplied by C1. Or we can say that C1 equals Q over K times 4 pi, which is a much more important analysis in this case. So now we have a term for C1. And now we can go back and apply it to this equation. We can say that Q over K 4 pi multiplied by 1 over R squared equals d of t. So the reason why I left this radius out is because we're actually doing this along two sides. We're doing this from the initial radius 1 and we're doing it for the outer radius 2. And then this is our temperature original plus whatever change of temperature they want, so I'll just call that T. So when we integrate both sides, we get a change of temperature equals, this would be Q over K 4 pi multiplied by, this would be 1 over R1 minus 1 over R2. Now, if you've noticed, we already have the change of temperature and Q. Remember, if we're talking about voltage in this case, voltage equals some current multiplied by resistance. Thermodynamics works in a very similar way. In simple one-dimensional analysis, uh, what is this? Our change of temperature, just change of voltage, our change of temperature equals some heat flow multiplied by some thermal resistance. So we have Q and we have our change of temperature. We just have to rearrange it so that we can get an expression for resistance. So we can just say that this is change of T equals Q multiplied by 1 over K 4 pi multiplied by 1 over R1 minus 1 over R2. And this part over here is our thermal resistance.